All right, here we are with working with our theorem again, the big theorem from Graph Theory 3. In the last video we did where k was equal to 2. Now let's look at k equals 3. All right, remember a cubed, let's see. This theorem defines what a cubed is. A cubed, it defines what it means for a graph. A cubed is a well-defined thing. Matrix multiplication is defined. But let's see, let's look at the entries for a cubed. As I've done before, you can think of a matrix like this as a grid. So you can think of it as you have V1, V2, V3, V4, V1, V3, V4. Even make it into a little table is fine. Something like that. And now we're looking, a cubed is, remember the a cubed ij is the number of 3-edge walks from vi to vj. So let's consider first this entry right here, v1, v1. This is the number that goes in there. This is the number of 3-edge walks from V1 to V1, from V1 to itself. Well, if you look at if you start over here in our graph here at V1, let's see how many different ways can we walk when we do a 3-edge walk and end up back at V1 itself. Let's see, you could do this one. You could also do this one. Those are 2 3-edge walks. So there's 2 3-edge walks. That's a 2 there. Now let's look at this entry here. This is the number of 3-edge walks from V1 to V2. From V1 to V2. So how many 3-edge walks are there from V1 to V2? Many of you are probably already saying, okay, I know what that is. Let's see, so from V1 to V2. How many 3-edge walks from V1 to V2? Let's see. You could do this way. That's 1. There's 1 3-edge walk. Is there any other 3-edge walks? Let's see. If you went out to V4, you could only go to V3, and then that's what we had there. Maybe if you went out to V3, and then went over to V2 first, then up to V3, and then back down. Okay, that would work, right? So there's one. There's another one. There. So you go over to V, so let's see, let me list the ones I have so far. So this is 3-edge walks from V1 to V2. So one of these is, as we found in red, was V1, V4, V3, V2. There's a 3-edge walk, 1 edge, 2 edge, 3 edges from V1 to V2. Another one, which I just found, was V1, V2, V3, V2. That's okay. Remember, a walk can have repeated vertices as long as these things are edges. There's an edge, there's an edge, there's an edge. So it fits the bill, it's okay. Let's see, what's another one? You could start at V, 3 edge walks from V1 to V2. So we did, how about V1, V2, V1, V2. Yeah, I think that'll work. So you got V1, V2, V1 over to V2, back to V1, and then back to V2. So this thing, 1, 2, 3. That's a 3 edge walk as well. Okay, is there any other way we could do that? 1, 2, 3, 4, no, I think that's it. So we've counted 3 there. So our answer here is 3. I meant to do that in blue. 3. And that's how these things go. All right, we're counting number of 3 edge walks. And so that's each of these entries. Let's just pick another one at random. Let's say, how about this one here? This is a cubed. Now we're going from V4 to V3. A cubed, 4, 3. That's that number there. That number that's going to go in there, that's the number of 3 edge walks from V4 to V3. So let's see. Oops, maybe I should go back to that. So from V4 to V3, how many 3 edge walks? Let's count them. You got 1, 2, 3. There's one of them. We've got 1, 2, 3. There's another one. And 1, 2, 3. There's another one. So there we go. There's another. I think that's just going to be 3 as well. Again, let's see. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2. Yeah, okay, I think that's it. So only 3 there. Let's put that in green. So that's that number there. And so that's how you'd fill this thing out.